it is chapter 6, orthogonality and least squares. In this chapter, we learn inner product, orthogonality, and orthogonal projections. And we'll apply them for Gram-Schmidt process, and particularly we'll try to get orthonormal basis, and we'll deal with least squares problems and regression analysis. Here we have section 6.1, inner product, length, and orthogonality. U and V are two vectors in Rn. Then the inner product or dot product, earlier you learned the dot product of U and V is defined by here. U dot V is U transpose V. So usually vector means a column vector. So transpose is a row vector and V is a column vector. So row and column multiplication, that is, the corresponding entries will be multiplied and sum. This is summation notation. U and V are given in R3, and we want to find U dot V. U dot V is the same as U transpose V. Here. So that is, now, okay, if we write down here, and 1, minus 2, and 3, and then vertically 3, 2, minus 4. Okay, so it's a row, column, or you may try to multiply the entries in the corresponding positions. So from here, this way, that way, that, and then sum. Okay, either way you can do that. This is 3. That is now minus 4. This multiplication is, okay, then must be 2, right? Okay, so it's a minus 8. So here we have minus 9. Okay. If U, V, W are vectors in Rn and C is a scalar, then now U dot V must be same as V dot U. It must be, because as corresponding entries are multiplied and summed, you can multiply the values, and in opposite order, it doesn't matter, the value will be the same. Now we have a distributive law, and here you can, after adding one's dot product, or separately you make a dot product and add them. For constant, the scalar, you can multiply scalar to one vector, or after dot product, just you can multiply C. Once you make a dot product, then this is a scalar. Now you can multiply C to the other vector. Either way, the result will be the same. Now, if you make a dot product, the same vectors, then U dot U, then always non-negative. It's quite easy to see. There must be U1 squared plus U2 squared, and then here last one will be UN squared. So it is non-negative. Once it is 0, then every entry must be 0, which means here U must be 0, right? Quite easily you can prove that. The length or norm, in this case, that is Euclidean norm, length or norm of vector v is non-negative scalar defined by in this way, and we are using two vertical bars both sides, and it's same as square root of v dot v, and that is this one, so that v norm squared is same as v dot v. And for any scalar c, and cv is the same as the norm of cv is same as v norm times absolute value of c. You have to be careful here. You have to put absolute sign. Okay. W is a subspace of R2 spanned by here a vector V34. Find a unit vector U that is a basis for W. Okay, once the W in R2 is subspace spanned by that one. Okay, let's try to visualize W. X is 3, Y is 4, there is 3, and this is 4, and a vector is given in this way, and that's V, and spanned by this vector is line including this vector passing through the origin, right? That one, that's the space W, the whole line passing the origin and including the vector W. Now find a unit vector U that is a basis for W. Okay, then here a vector on the line having length 1 will be a basis, so that from here we can find U from V by scaling, so the V over V length, then the result will have length 1. Now what is the length of V? From Pythagorean triple, we know that one side is 3 and the other is 4, then hypotenuse of the right triangle is 5, right? So that the length is 5. Okay, so here we have 1 over 5 and V. Okay, we can rewrite here 3 over 5 and 4 over 5. That is a vector, or the negative direction, the opposite direction also will be a basis. Either this one or that one will be fine. Distance. U and V are in Rn. The distance between two vectors is defined in this way. This distance UV is the same as norm of U minus V. So that is the length of U minus V. Okay. Now let's try to compute the distance between vectors U and V. Then if we are using the formula, then first we make U minus V. Okay, then U is 7, 1. Okay, let's try to write down detail, 7, 1. And V is now 3 and 2. So that one is 4. Now the second one is minus 1. Right? So norm of this vector U minus V will be squared, summed, and square root. So the square root of 17. So that's the final answer. Now pictorially, we can explain the distance in this way. That's U. Now that is 7 and 1. That is U. And that is V, which is 3 and 2. Now here, if we see u minus v, then first we go up to u, and now v is this one, and minus v is opposite direction. So we try to move exactly this way, the same direction and same distance, and then we reach that one. So that is u minus v. And if you try to measure the length, then u minus v norm is this one. Now, from this parallelogram, we know that this length and that length is the same. So eventually, that length will be u minus v norm. So pictorially, we can say that here, the u minus v norm, the distance is really distance between these two. So these two endpoints, then we can measure the distance. But by using vector notion, and in fact, u minus v must be go over there and that one, and the norm is this one. But from this parallelogram, this is the same as that one, right? Okay. In this way, we can interpret the concept of distance between two vectors. U and v are given, and we want to find the distance between u and v. The same way, just we first organize u minus v, then here corresponding entries will be here subtracted, so that minus 2, this subtraction will be minus 4, that subtraction will be 6. So minus 2, minus 4, and 6. So that from here, u minus v norm is same as square root of the component squared, 4 plus 16 plus 36. So that is 40, and now square root of 56. Right? Okay. The inner product can be defined as, in this equation, u dot v is the same as u norm and v norm times cosine theta. Theta is the angle between the two vectors. So that here, okay, now we have u and v. Okay, that is, this is origin, and that is u vector, and that is now v vector. Then, and that is the angle between two vectors, and dot product is now this length times now the length of v and cosine theta. Okay, so there it says right angle. Then this portion is the same as v now cosine theta, right? So once length of u is 1, then this inner product is a kind of projection, so that we try to find the component in u direction. So just by normalizing u, the length is 1, we have now that is a v norm times cosine theta, so that v is projected into u direction, and the component is found. So that can be used as a definition for inner product. Some textbook is using this equation as the definition, but we'll use it here. Okay, u and v are given, and use the equation to find angle between u and v. Okay. Now we have to get u dot v, u norm, and v norm. Then we can find the cosine theta. So what is u dot v? That is, now the corresponding entries are multiplied. First one is minus 1/2. Second one is now 3/2. So that is 1. Now u norm, that is here 1, the square, so that is 1 plus 3, so that is 2. Now v norm, okay, that one is square root of square sum, 1/4 plus 3/4. Okay, the sum is 1, so that's 1. That means here 1 equal 2 times 1 and cosine theta, which means cosine theta is half, so we can conclude theta is pi/3, right? And 60 degrees. Okay. Okay, now we'll continue in the second part. Thank you.